Hello and welcome back. Today we have 191 number of 1 bits. It says here to write a function that takes the binary representation of an unsigned integer and return the number of 1 bits it has, also known as the Hamming weight. So given an integer, let's say we're given 11, we take its binary representation, which is this string here, and we return the number of 1 bits. So there is a easy way to do it, which is not their recommended way, but I'll show you that just to show you that there is that way, which is, okay, so we're given this, which is 11. Just to confirm, we can do int of the binary string, it's binary, we're given 11. All right, so our input is 11. Given this input, we can convert it into a binary string by doing this, and we can convert this into a string by doing that, and then just count 1. So that's of course one way. That's not their recommended way. The recommended way is actually to knock out ones one by one. So going from the least significant bit from the right, going left bound, it is to knock out all these ones. So if we take the example of 1011, the way they do it is by taking, by using the AND operation, which is where both must be 1 to equal 1 if, either of the two are not ones, or if both are not ones, these all equal 0. By taking the number just below the starting number, we essentially get the last bit flipped. And when we AND this, then anything to the left stays the same. However, anything from the current position to the right gets zeroed out. So 1 and 0 is 0. Okay, so that was one operation to zero out this guy. So now we have this. So 1010, and the number just below that would be 10. Now we move this to 0, then this gets carried over to 1. Okay, so now we're working on these two, which means that everything to the left stays the same. However, from the current position onwards, these become zeroed out. That was their second operation. All right, we have this number here. So when we have this number, the number just below that is where we flip this to 0, and then all of these become 1s. This is the number just below this one. Then, by the AND operation, we end up flipping all of these to 0, and that took us exactly 3 operations, as we can see here. So essentially, whenever we have a number, so let's take this big one, for example. When we have a number, whenever there's a 1, it takes us 1 operation to make every number on that current 1 and to the right of it into zeros. So here we already have a 0, so we'll be skipping these, and all of these remaining will take exactly 1 operation each to make it a 0, or to zero out. So if we take this shorter example here, it's getting a little hard to see. 1, 2, 3, 4, 5, 6, 7. Okay, So let's say 1, 2, 3, 4, 5, 6, 7. The number of zeros actually don't matter, but let's continue. So here's our 1. The number just below this is where we make this into a 0, and all of these become 1s. Then when we apply the AND operation on them, we end up zeroing this out. So this all becomes 0, and this took oh no, come back. This exactly took 1 operation. And that's basically the trick. Starting from the least significant bit and going left bound and zeroing out each one, where zeroing out action takes exactly 1 energy, and then that becomes our output. So in code, let's see, there we go. Okay, so we start with a count. We're going to be counting the number of operations it takes to zero out this entire input, or essentially count its 1 bits. And we can say, while there is a number, while this number is not a 0, while it is greater than 0, we can take that number and apply the AND operation on the number just below itself. Okay? Just below itself. And then we can also increment our count. So by the time number becomes a 0, where we've zeroed out all the 1s, we have the total count of operations it took in order to zero out entire number, or also to count its number of 1 bits. And yeah, I mean, that's basically it. We return the count, we can submit, and this is their recommended way. I don't know if this was very helpful, but for me, it was a bit challenging to understand this, where the main idea is they're starting from the least significant bit and they're just zeroing out each one. And using the AND operation, whatever one you zero out, so the digit that you're on, let's say this is a better example. Let's say there were zeros here. Whatever digit you're on, when you take the number that's 1 less than itself, and then you AND that subset, starting from the digit you're working on, that gets zeroed out. So we're using this in order to count our 1 bits in an efficient manner. I hope that was helpful, and once again, this was 191, number of 1 bits. Thanks so much. Happy coding. See you next time.